So our first speaker this afternoon is Dzmitry Dudko, who will speak about boundaries of disjoint-type hyperbolic components.
Thank you. It is a pleasure to finally visit India. Yeah. So this is one of our favorite set. It's called the Mandelbrot set. And here is the main hyperbolic component. So this is the set of polynomials obtained by deforming the square. And as we know well, this is a disk, a closed topological disk. If we okay, let me try to blow up. Okay. Okay, so as I was saying, this is the main hyperbolic component of the Mandelbrot set. It is a closed topological disk if we add the boundary. And for quadratic polynomials, we know a lot about the boundary, and it has various features. So for example, if we zoom here, then we would see elephants going out of the cusps. So and this is the Julia set of the cusp. So if we zoom somewhere here, we would see this pattern. And then if we continue zooming in, this pattern stabilizes. So and this is another self-similarity feature of the boundary of the Mandelbrot set. And this is the golden Siegel map at which we zoom in. But today I'd like to talk about hyperbolic components in the space of rational maps. And it is well known that the hyperbolic component of this square in the space of rational maps is not bounded. And in fact, the boundary can be explicitly computed. So I'd like to first review this example. So this would be the main motivating example. As I said, more or less everything is known about this hyperbolic component and its boundary, but we can still add a little bit more. And then the main message is that a lot that is true for this hyperbolic component is also true for a general disjoint type hyperbolic component in the space of rational maps. So let's start with definitions. So we are looking at a rational map, which is a hyperbolic of disjoint type. So in particular, it has 2D minus 2 attracting periodic cycles, the maximal number of attracting periodic cycles. So for convenience, we add a bit of markings. So we mark fixed points to prevent finite order symmetries. And then we can look at multipliers of these periodic cycles. So if a cycle has period, let's say pi, then the multiplier is just the derivative at one of the points at the cycle, doesn't matter which. So we have 2D minus 2 multipliers, and then they do parametrize our hyperbolic component. And we can identify our hyperbolic component with the unit disk in this power. And the parameterization is via the multipliers. And in order to justify such a parameterization, we can just appeal to the rigidity. So two maps are complex conjugate if and only if the set of multipliers coincide. So we would like to take a look what's happening with this parameterization as we approach the boundary. So for that purpose, let us introduce what we call the regular boundary. So this is all maps on the boundary of the hyperbolic component so that no gamma I collide. So in particular, we still have two d-2 distinguished parameters. So this is the subset of the boundary where nothing goes bad with the parametrization. The complementary situation is what we call exceptional boundary, where we have doubly parabolic collisions. So this is the set of maps where at least two of our cycles, now they would become neutral. So if two cycles coincide, then we call such situation the exceptional boundary. So the collisions happen within lower dimensional strata. Let us also define the geometrically finite or rational boundary. So this is a set of maps where we have only attracting and parabolic domains. And let us also define the obstructed boundary. So this is going to be the subset of the formal boundary using our identification. So and this is the set of multipliers that are not accessible. Or saying more precisely, so we would like some sequence of maps that go to infinity so that the multiplier of this sequence goes to our abstracted parameter. So as I said, the parametrization of the hyperbolic component by multipliers is kind of easy to justify, but the parametrization on the boundary is becoming more tricky, but still there are tools, like they are called transversality, initially introduced by Adam Epstein and then by Levin. So in particular, transversality tells us that at least with the regular boundary, everything is good. So the multiplier map is injective on the regular boundary. And on the level of multipliers, the regular boundary is disjoint from the exceptional boundary. So in particular, we can claim this property. So just to kind of summarize what I said. So if H is disjoint type, then this is the same as 2D minus 2 attracting cycles. And what we would like to say is that in this case, the boundary, the nice boundary, is approximately the boundary of the disk to the power 2D minus 2. So this allows us to identify the hyperbolic component with the corresponding unit disk. So minus the obstructed boundary. And here we ignore the exceptional boundary. Which is within lower dimensional strata. So this is kind of the main summary of this slide. And let's discuss the example z-square in more details. So the Julia set is topologically a circle. So here we have the infinity. And the lambda infinity is the derivative at our fixed point. And similarly, lambda naught is the derivative the zero cycle. And we also have another fixed point which is on the boundary of both attracting domains. So and we can also look at the multiplier. Well, it turns out that at least in the case when the degree is true, these are good parameters, the multiplier parameters. So we have 3 parameters, but there is a relation, and this is the relation that is coming out of the holomorphic index formula. So one of the multipliers can be obtained from the other 2. So in particular, this formula tells us that lambda naught times lambda infinity is never equal to 1 unless they are both equal to 1. So if they are both equal to 1, then denominator and numerator, they are 0, and lambda 1 is a free parameter. And this corresponds to the exceptional part of the boundary. So this is the exceptional part of the boundary in the lambda 1 plane. But yeah, as I said, I'd like to mostly ignore the exceptional part. And this formula kind of takes this form. So the regular boundary is the full boundary minus the obstructed boundary, and the obstructed boundary is this one. So this is we can write it as lambda and lambda minus 1.
What kind of obstruction do you allude to?
I'll try to explain it later. But Thurston obstruction is a good motivation for my talk. So
the limiting map is not particularly finite.
Yeah, the limiting map is not critically finite, but still we can view it as a certain abstraction. But for example, when phi is rational, then we have 2 fat rabbits, and then it's a regular abstraction. So when these numbers are rational, then it's a regular abstraction, and for irrational, we would like to think of irrational abstractions as limits of rational abstractions.
So when you say boundary of hyperbolic component,
Yeah.
is it in the moduli space or the compactification?
Yeah, when I say the boundary, well, the regular boundary, I'd like to view it inside the space of rational maps, but with markings on critical points. But I would like also to view it formally. So using the multipliers, we can identify the hyperbolic component with the unit disk in some power, and then we can ask for like a formal boundary. And we can ask whether some parts of the formal boundary can be realized in the regular modular space.
On the upper right, you have dimensions.
Yeah.
Could you go through those dimensions?
Yeah, so this is, let's see. Yeah, so this is the full dimension of the hyperbolic component. Yeah, I should have put. Yeah, so this is the dimension of the boundary. So this is the dimension of the abstracted boundary.
Recording in progress.
And this is the dimension of the exceptional boundary. So this is the dimension of the exceptional boundary. But if we evaluate the multiplier map for the exceptional boundary, then we'll just obtain 1 point. So under the multiplier map, the exceptional boundary collapses into 1 point. So another way how to view the exceptional boundary is that we take the formal boundary and do blow up. So we take the formal boundary through the multipliers and make a blow up. Okay, so let me make a small comment about markings of fixed points. So as I said, it's convenient for us to mark to prevent finite order symmetries. But since we do mark, there are kind of free hyperbolic components in the marked space of rational maps that correspond to the square. So because we have free fixed points and there are free pairs, and two of them can be attracting. So this is roughly the arrangement in the space of marked rational maps. And if we go down to the regular space of rational maps, then this image will not be simply connected, so it will be some hyperbolic component with self-touchings. Kind of, yeah, it's difficult to imagine in dimension 4, but at least something will happen. So, and that's kind of one of the reasons why we introduce markings on the fixed points. So this is Milner's approach, and this breaks symmetries for hyperbolic components. But in the space of rational maps, we can introduce this type of coordinates, so they are Milner's coordinates, and then they can be used to compactify the space of rational maps by compactifying C-square. Okay, so let me also mention the dynamical plane. So we may view our hyperbolic component of the square in the space of rational maps as the mating of polynomial hyperbolic components. So on the levels of multipliers, this would mean that we have multipliers of 0 and infinity, and we split them into lambda 0 and 0 and lambda the infinity 0. So at least on the level of the multipliers. And for the hyperbolic component itself, it's not a problem to justify such a mating. It's also not a problem to justify for some maps on the boundary. For example, when lambda naught is attracting and lambda infinity is neutral. So it's known that mating exists for rational boundary. So if we have P over Q and A over B, and now I'm kind of switching into rotation numbers. So I'm kind of assuming that lambda naught is e to the power 2 pi I phi, and lambda infinity is e to the power 2 pi I psi. So if phi and psi are rational, then the mating exists, unless there is an obstruction, unless one is the negative of another. So this is by Mary Rees, Stanley, and in fact they proved it for postcritically finite maps in limbs of the Mandelbrot set. But the mating also exists for Siegel maps of bounded type on the boundary. So if phi and psi are of bounded type, and I'll give a definition a bit later, then the corresponding quadratic polynomials can be mated. Kind of, and this is from the movie by Arnaud Cherita. So he has many movies. In particular, one of them is about mating of Siegel polynomials. So we can assume that this is 0 and this is infinity. So this would be Siegel disks. So the postcritical set will be kind of on the boundary. So this is the postcritical set. And as we can see, there is a separation between the postcritical sets associated with 0 and the infinity. And in fact, we can claim such separation for all neutral maps. So namely that there is a separation in terms of the combinatorial distance between phi and minus psi. So this is kind of another way how to look at the abstraction. So when our phi and psi becomes more unbounded, these nice QC disks, they will become less QC, so they will become more like amoebas. And in the limit, they can become Kramer hedgehogs, for example. But still, we can claim the separation of these postcritical sets. And this is the separation is in terms of this distance.
What exactly is that distance?
Just a combinatorial distance, so distance in the circle. And I'll try to explain the reason why it comes in.
So can you say something about the modulus of the envelopes of this range?
Not explicitly, but just some function. So the modulus would be greater or equal than some function that depends on this, but not explicitly. Oops, yeah. Yeah. Okay, and these are the theorems. So they're joined with Yushen, Liu, and the second is in progress. So the message is that what happens for this square happens for general disjoint type hyperbolic components if we look it from a certain angle. Kind of namely that if our map is Sierpinski, then in fact there are no obstructions, and the whole closure of a hyperbolic component is a polydisk. And there is also no exceptional boundary. So in the Sierpinski case, there are no obstructions. There are also no obstructions in many other situations. And the way how we can try to state is that kind of this obstructed boundary should be the closure of geometrically finite obstructed boundary. So, for example, in this formula, again ignoring the exceptional part, we can rewrite it as the boundary minus the closure of geometrically finite obstructed maps. Yeah.
When you talk about the closure of a hyperbolic component, this is the closure in the topology on the moduli space, or in what sense?
Well, on the right, it's on the formal vault. So here, so this is identification via the multiplier. So in particular, here is the formal boundary, the boundary of the closed unit disk in this power, and we can define the abstracted boundary kind of a hyperbolic component. So namely, this is the part that does not correspond to the actual boundary.
So the parametrization,
Yeah.
what kind of regularity? So we stay inside the polydisk.
For the regular boundary, it will be an analytic parametrization. Yeah, so multipliers depend analytically. So if it's either analytic or there will be something drops.
Which brings me to the second thing that confuses me.
Yeah.
These cycles themselves are not distinguishable.
Yeah.
So when you pick the parameters,
Yeah.
when you pick the multipliers, they are really not distinguishable. So one is actually looking not at the polydisk but the symmetric.
Yeah, this is why we introduced fixed markings on the fixed points. So without markings on the fixed points, there will be a finite order symmetry quotient. So we would like to ignore it, so and therefore we introduced markings on the fixed points. But yeah, in the actual parameter space, the life is more interesting. But we wanted to ignore these issues. So in particular for the z-square, the statement is that the abstracted boundary, and this is the full abstracted boundary, is just the closure of rationally abstracted boundary, which we understand. And in the dynamical plane, well, if our map is Sierpinski, then there are regular quadratic-like domains, and we can use a quadratic-like randomization to identify the corresponding hedgehogs with the corresponding hedgehogs of a quadratic polynomial. But in general, we can use sector randomization to make the relation with what's happening to quadratic polynomials. And let me also mention that simultaneously Jeremy Kant announced an independent approach. So there are MSRI videos of good quality available with his approach. So his approach is also in the near-degenerate regime, but from a completely different angle. So in particular, his approach works for Sierpinski hyperbolic components of any type, not necessarily disjoint. But it seems that in his approach, Sierpinski is a necessary assumption. So he really uses the fact that for two components are disjoint. And this is the Macmillan conjecture that was motivated by geometry of free manifolds. So in our situation, we look at Ziegel disks, so I'll tell more soon. And we understand how they come, we analyze how they come close to each other, and therefore we can say more for the non-Sierpinski situations, but we really work in the disjoint type. And before that, little was known in the space of rational maps. So there were some cases where the complex dimension of parameter spaces was true. So namely, Adam Epstein shows that disjoint type hyperbolic components in degree 2, which are not polynomial, are bounded. So in particular, some of them are not Sierpinski. Yeah, and later, Nie and Pilgrim kind of extended this approach with new ingredients to some other cases. But these are restricted spaces. So they are not full parameter spaces. Okay, good. Maybe it's a good moment for questions, if there are, about the statement. Yeah.
Not exactly the concluding statement, but about the slide itself. Still sort of curious that when you look at the abstract boundary or the formal boundary,
Yeah.
How does it sort of compare? What does the formal boundary look like within the character within the moduli space?
Well, the way how we can think, at least how I can imagine for myself, is that we have a formal boundary, and then the abstracted boundary should go to infinity. So the abstracted boundary lives at the infinity. So if we introduce some good compactification of the modular space, then there will be obstructed boundary, but it would just leave edge infinity. And the exceptional boundary should be blown up, whatever blown up means. Yeah, but the square gives, well, the case of the square gives already a lot of motivation, and it illustrates more or less all the cases. Okay, so let me say some ideas in the proof. So the proof uses near-degenerate approach, and various ideas of the near-degenerate regime can be traced to the work of Bill Thurston on free manifolds. So in particular, we know quite well that if we have a compact surface, then a compact surface degenerates along thin annuli. And this has been used successfully by Bill Thurston to prove some compactness results, both for free manifolds and also for post-critically finite rational maps. But there is an analogy of synthetic decomposition for open sets in the complex plane for surfaces with boundaries. So namely, if we have an open set of finite type, then the only way how it degenerates is by developing white rectangles. So for example, if we look at these two components, if they start to degenerate, then we can look at the set of curves that connects them. So this is the set of curves. And the statement is that all of them except some additive constant that depends on the complexity will be in finitely many disjoint rectangles. So there will be finitely many disjoint rectangles that witness how an open set of finite type degenerates.
Because it can also degenerate along thin annuli.
Yeah, and then another possibility is along thin annuli that surrounds some hole. Yeah. Yeah, many people say that to relate this true, we can just mirror this picture, and then when we do the mirror, we produce a compact surface. And to go from here, we just cut in half. Well, and this was also productive in the renormalization theory of quadratic polynomials and beyond. So Jeremy Kahn was the one who introduced these ideas to the renormalization theory. Together with Misha, they introduced basic tools to work in such near-degenerate configuration, and they established various a priori bounds for quadratic-like renormalizations with the consequence to the MLC conjecture. Well, together with Misha, we used near-degenerate regime to obtain uniform a priori bounds for quadratic polynomials. And yeah, so as I said, that sets in the complex plane, they do degenerate along white rectangles. But since we are interested in the homotopy types of these white rectangles, it's more convenient to change the picture and make white rectangles narrow. So let's say that we apply a Photoshop, and then everything that was white before becomes narrow. So at least for narrow rectangles, we understand better on pictures the homotopy properties. Okay, and then let me try to illustrate sort of the main idea on the case of Z square. So let's say that we have a map F on the boundary of Z square in the space of rational maps. Let's assume that one of the multipliers has rotation number phi and another has rotation psi. So let's first assume that phi and psi are of bounded type. So and this is the definition of being bounded type. So just to kind of put it back. So this is the infinity, this is 0. So as I said, in the bounded type, it was Michael Impolsky and Said Zakeri who show that the corresponding disks are QC. Kind of our goal, sort of the main goal, is to bound the modulus between these two disks. So we have a boundary here. We have a boundary here. And we look at the degeneration. So in particular, we look at, let's say, 1 over mod C hat minus Z naught plus Z infinity. And this is going to be degeneration or width between the corresponding disks. Yeah, and let's call it K of phi psi. And the goal is to bound it in terms of some function that depends on the distance, on the combinatorial distance between the rotation numbers. Yeah, and of course, we want that this is independent on M. So namely, kind of once we have such a bound, then we can let our rotation numbers to grow in the arithmetic complexity, and we would still have a separation. And once we have such a property, then we can also kind of introduce sector renormalization and then try to identify it with what's happening with quadratic polynomials. Okay, so this is where the condition on distance come into the story. So let's assume that the degeneration between these Ziegel disks is represented by a white rectangle R. So and remember that narrow on picture means white in reality. So in reality, this should be kind of very white. And we are going to look at how such rectangle lifts under the map F. So the statement is that since the rotation numbers are different, so we have a different speed around 0 and infinity. So therefore, there will exist such a pull-off constant that depends only on the distance. Such that if we try to lift this rectangle under the map F, so the first lift may still connect two Ziegel disks. The second lift may also connect, but still there will be some moment, namely this capital N, where it cannot connect the Ziegel disk at infinity with the Ziegel disk at 0, because of the speed, this would eventually want to cross the original rectangle R. And white rectangles cannot cross. So this is where the condition on the combinatorial distance comes. So in particular, if the pull-off constant is equal to 1, then this should be a configuration of lifts of R under just one iteration. So under just one iteration, there will be two pre-images, and one of them is this one, and another is like this. So we should not see a pre-image that connects directly. So if the pull-off constant is 2, then under the second iteration, there will be no rectangles that connect two Ziegel disks. So one of the pre-image would perhaps connect the node with a preperiodic pre-image. So now if we look, so we can look next as how the surface here embeds here. So namely, we look at how this embeds into C hat minus the node plus the infinity. And what we can deduce is that kind of curves in this rectangle, or saying it slightly simpler, that this rectangle should travel through the pre-images of R. So namely, curves in R, for example, they can start here, then kind of then go to this bubble, then do something in this bubble, and then cross into the node using the pre-image of R. Well, now we can use it. Yeah, let me try to kind of say more words. So by analyzing such a picture, we can claim that a substantial part of R hits one of the preperiodic bubbles. So if this is R, so let's say that this is the infinity, this is the node. So this is R. And then a substantial part of R hits a pre-image, let's say, of the infinity. So n will be less or equal than the capital N. So we can localize quite effectively on a very small interval and find degeneration, which is part of the this white rectangle that passes through such interval. And then we can apply our f, well, f to the power n. We can bring this interval together with a degeneration to the infinity. And then, since it's small, so we can assume we can make this interval sufficiently small. So after that, we can also spread it around. So along the boundary. And this way we can produce bigger degeneration. So just to put some quantifiers. So if the original rectangle had width k, then this new degeneration kind of can be constructed of the order of some constant that depends on n times k. And then it can be spread around qm times, where q sub m is one of the closest return. So in particular, new combined degeneration here could be made bigger or equal than q times qm, c of n, perhaps some other constant, times k. Okay. So which would be much bigger than the original k. So what happens is that we are writing down such an inequality, and then at the end we just say that this inequality work starting with a certain threshold. So if the original degeneration was sufficiently big, and sufficiently big would depend on this capital N on m and eta. So there are these constants that appear, and these constants that appear, we can beat them by allowing k to be sufficiently big. So this constant affect k indirectly. So and this kind of leads to a contradiction. Okay, so this is kind of some ideas how to produce a contradiction. But combinatorial reason, as I said, is that since we have a different speed, h0 and infinity, eventually a white rectangle cannot persistently connect these Ziegel disks more than n times, capital N. Okay, yeah. Okay, this is what I kind of wanted to say about kind of ideas behind the argument. Any questions? Yeah. Comments?
So the overall logic, so you have some degeneration in between the guys, and then you produce the bigger degeneration in between themselves. So, or
Yeah, it could be, in fact, two possibilities. Either it will be between themselves, or degeneration would go deeper, and then we'll use our a priori bounds for quadratic polynomials. So a priori bounds for quadratic polynomials kind of are hidden in understanding deeper scales. So what we need to do is to analyze the interaction on top scales between z0 and z infinity.
you go to deeper scales if this rectangle go inside of the
Yeah.
polydisk.
Yeah. So yeah, I wrote it like this, but in fact, yeah, in fact, in order to properly localize it, we would already need to work with pseudo-Ziegel disks. So I did, hide a lot of activities. Yeah.
Did you make any assumption about the homotopy type, homotopy class of this curve joining?
No. So here it's just an annulus. So in fact here, kind of our rectangle is the full annulus. So kind of the statement just means that kind of we have an annulus. It has a lot of vertical curves, and then eventually these vertical curves, most of them would be pulled off with respect to geometry. Otherwise, a lot of vertical curves would cross the lifts. There are no kind of homotopy assumption on rectangle A. So in the case of the Sierpinski maps, so as I said, this approach works for disjoint-type hyperbolic components, and in the case of Sierpinski maps, such pull-off constant can be globally bounded. So in fact, we can sort of consider the corresponding constant for the PCF model, and then it's uniformly bounded. And the reason is the following. So let's assume that this is our Sierpinski carpet, and this is the postcritical set. And we can look at two. Yeah. Okay, so let's say that this is point A, and this is point B. So no, it's not. Is it better? Yeah. Okay, good. Okay, so the corresponding statement for Sierpinski carpets is the following: that suppose we have two points in the postcritical set, and let's assume that they are fixed for simplicity. Then we can ask kind of for persistent arcs that connects these 2 points, like gamma 1, gamma 2, and so on, gamma 3, gamma 4. So with the property that gamma n plus 1 is a preimage of gamma n, and they are simple and disjoint away from the fixed point. Then the number of such arcs is bounded in terms of the complexity, in terms of the postcritical set, and perhaps degree. I guess degree we don't need even. So yeah, and we should think that simply and disjointness come from properties of white rectangles. So if we bring such properties into the PCF model, then we'll get this assumption. Kind of, and the argument is that kind of they cannot be homotopically equivalent, because once if gamma 4 is homotopic to gamma 1, then this would mean that we have a periodic arc between 2 postcritical points, and this would mean that the corresponding for 2 components touch. And this is not the situation of a Sierpinski carpet. So in Sierpinski case, the disjointness of for 2 components means that such a quantity is uniformly bounded. Yeah. And in fact, for the PCF model, this is a characterization. But when we talk about boundaries, then this can still be, well, as I said, for non-Sierpinski case, hyperbolic components can still be bounded in the parameter space, but this needs not to be bounded. So this is where the condition of Sierpinski carpets come. Okay, let me now just stress kind of the main steps of the full construction. So as I said, we are looking at the disjoint-type hyperbolic component. So it has the center, and the Thurston realization theorem allows to claim the center. So the center we can realize by a classical Thurston theorem. And then, for example, by doing QC deformation, we can realize all maps in the interior of the hyperbolic component. Well, there is an extension of Thurston theory towards geometrically finite maps that have attracting and parabolic components. So, for example, one can use Kosinski argument. Misha mentioned it during his talk. there is approach by Tsui and Stanley. There is approach by Yushen Liu. So all of them should work for disjoint type. Well, Hasinski approach was originally for polynomials, but it can be generalized. Kind of. So in particular, it means that we can kind of suppose we have a map F on the regular boundary that we wanted to realize. So we know for combinatorial reasons that it is realizable, and we can try to realize it properly. So what we can do, we can first approximate it combinatorially by geometrically finite maps. And we assume that for attracting cycles, we have just equality between the map that we wanted to obtain and its approximation. And for neutral multipliers, we have approximation. So this we can do. Well, then then we wanted to perturb parabolics into bounded type Ziegel disks. So we can first do it formally, sort of just by saying that each parabolic multipliers can be slightly vibrated. And then we can use the result by Zhang saying that since the rotation number is of bounded type, the Ziegel disk that we obtain would be nice. So in particular, it would be a QC disk when we add the boundary, and it will have a critical point on the boundary. And we can also kind of control such a perturbation from the homotopy viewpoint. So what kind of can go wrong is that here we have a parabolic flower, and here are some other domains. And in principle, when we do perturbation into a Ziegel disk, sort of the new Ziegel disk may start to do something wild in principle. So it may change a homotopy class. But yeah, this can be controlled, kind of, and prevented. So there are enough tools. So for example, using hyperbolicity of renormalization. And yeah, I'm not sure if it can be used without hyperbolicity of renormalization. So these statements are kind of almost obvious, but usually difficult to prove. Kind of, and then the last step, kind of the main step, is that we wanted to claim that such a sequence Fn satisfies a priori bounds, namely we can take the limit. Well, and for that we are kind of using this type of arguments. Kind of, at the end the control of degeneration can be expressed in terms of such Pulov constant n of Fn. So this is a combinatorial Pulov constant. And also the degeneration will depend on the multipliers of attracting cycles. Okay, so this is gamma. But these are frozen, so we freeze them. Yeah, and as Misha pointed out, there are two possible degenerations, kind of a Riemann surface with a boundary. So first degeneration can be along a white rectangle. or something like this. And this is, in a way, the main the case, and this we deal it with this type of arguments. But also, we should take care about loop degenerations. So these are arc degenerations. And these are loop degenerations. And then they can be dealt more or less as while following some ideas from the original Thurston theorem. So meaning that if there is a loop degeneration, then we wanted to claim that there is an obstruction, and this obstruction also exists for a PCF model. So and then there has been various developments of methods. So in particular, a convenient way how to do it is to analyze what's happening at the limiting tree of spheres. So namely, if there is a loop degeneration for sequence Fn, then we can go to the limit and analyze the limiting tree of spheres, and then say that such degeneration would imply a Thurston obstruction for the PCF model, which would be a contradiction. Okay, I guess my time is out. Okay, thank you.
You have a few more minutes because you had a lot of questions.
Well, we can have more questions now. Yeah. Okay, thank you.